Okay, so this morning I explained non-equilibrium steady states and gave an example in conformal field theory. So now the point is I'd like to go further beyond CFT. So in CFT, we could do all the computations explicitly for the VR0 sector. And but in general, it's much harder to do computation explicitly. I mean, it's a hard problem, right? So you have initial state, which is quite non-trivial, with different temperatures left and right, which is not stationary, and you evolve with an interacting many-body Hamiltonian. This is just a hard problem. But it turns out that there are very strong techniques, techniques that allow you to get quite strong results. And I want to show kind of, first I start with one kind of small general inequality, set of inequalities that we can write for stationary state averages. Just some general inequality that comes from, I mean, it's not a complete general proof, but some general physical principles. So it's something we can write without having to know too much about the macroscopic systems. And then I will talk about the hydrodynamic ideas, which are physics ideas. You can use hydrodynamics to derive stuff, and that really allows you to calculate a lot of things. And eventually, with hydrodynamic ideas, one can go, well, in principle, to interacting systems. Although, of course, then it can be complicated to have something explicit, but to integrable systems where you can have something quite explicit. I don't want to go into too much of the details of integrability and all that. I mean, I don't want to be technical here, but explain the main ideas, and I can illustrate everything even with free fermions and see how it goes and generalize to integrable systems in some way using known results from beta ansatz without having to derive beta ansatz results. I'm not going to derive any beta ansatz thing here. Okay, so the first thing I start with is some kind of general bounds or inequalities. So remember we have now, so we still think about T left, T right, if you wish. Then think about more complicated, but we have T left, T right, and the system there, and we let time evolve, and we look at stationary state far in time, right? So yeah, I don't know if my pictures in my here are inverted, so I'm gonna have now time go upward instead of backward, if you allow me. Otherwise, I get very confused. Okay. So, yeah, so this is T left, T right, time evolve like that, and we want to know what's happening. Now we know that there is some kind of light cone, right? So beyond that is still T right, there is still T left, and something non-trivial is happening in here, and then we don't know what's happening. So there are certain inequalities that we can write for our basic quantities, okay? So I'm still thinking about the stress energy tensor, and I'm still thinking about relativistic theory, say QFT, relativistic QFT, right? So I still have some energy density, some current of energy, which is the momentum, because it's relativistic variance momentum, and some current of momentum, which I'm going to call K here, just to give it a letter, okay? In CFT, this is equal to H, then I have simplification. But in general, well, I don't know what that is. This is just some other operator, right? I can write explicitly the operator in some given theory, but it's something complicated, right? So these are just local operators. It takes some form, and it doesn't matter too much what form they take. Okay? Then I calculate their average in this initial state, evolving time in space-time. Look at what happens in space-time, okay? And I know that these will satisfy some continuity equation because they are, conserved current, right? So I'm going to have this continuity equation for the energy that involve the average energy density momentum, and continuity equation for the momentum itself, so momentum continuity, and that's going to be involving the average of the momentum current. What's the momentum current physically? Do you know what's the momentum current physically? Physical meaning of that? Current of momentum. How the momentum changes in space or something. Force, yeah, precisely. It's a force, actually. It's a pressure, kind of, indeed is precisely that. So this is some pressure quantity. It's even under time reversal, for instance, like the energy, right? It's some kind of some simple quantity, but it's it is a non-trivial function of xt, and I don't quite know what it is. Okay. Now so the inequalities that one can write is the following, and this is in relativistic QFT with velocity 1, but one can change the light cone velocities. The formula will change, but for now I take it to 1. So the inequality is that if you take the average of the energy density on the left minus the average of the energy density on the right, divided by 2, that always is greater than the average momentum in the stationary current in the stationary state. So that's a lower bound. It's an upper bound for what the current in the stationary state can be. It depends on difference of energies on left and right. Of course, if the energies are the same, there's no current. But I mean, this is a lower bound. So somehow the current must be, I mean, cannot be too much. Cannot be too much. If the current is too high, I mean, you have to have a big energy difference. More interestingly, there is also a lower bound for the stationary current, which is determined by these pressures. So K left minus K right divided by 2. So there must be a current if the left and right pressures are different, which is natural, right? Because you have pressure there, more pressure there and less there, you're going to have a non-zero current. Okay. So there's these general inequalities that should be satisfied. It's smaller or bigger or equal. Okay. And in CFT, you can check in CFT, because now K is equal to H, of course, you have equalities on both sides. So these two bounds are exactly saturated. But in general, these are bounds. We don't quite know exactly. So the stationary current, average momentum, is not just simply determined by the pressure or the energy like it is in CFT, it's marginal. So why is that this bound? Well, you can argue for it, not complete proof, but you can argue for it like that. So you have, again, your T left and T right there. And you have this like cone like this, okay? And you write, I'm going to do just the second bound, just the first bound is something similar, okay? So I'm going to use this one here. So, and you consider that continuity equation for the momentum, continuity equation for momentum, okay? So this is momentum density, which is also the energy current. So this is what allows us to calculate something about the current, because the current of energy is itself a conserved density. And that's, so, okay, so there is this continuity equation, and we have that structure like that. And what you do, you just write the global form of the continuity equation. So you kind of integrate that over space-time. So if you integrate that over x and t, when you integrate that over x and t, you use the t derivative, you're left with just x integrals. And when you integrate this over x and t, you're left with just time integrals. So you're left with a contour integral, right? And the contour integral is something like that. Yeah, something like this, like this, like this, like this. Okay. And so explicitly in equations, I have something like this. So I would have integration, say I put minus L and L here. So from minus L to L, dx of the average momentum at x t minus at x0. So I'm going to go all the way up to t here. And this must be equal to the integration from 0 to t of the average pressure. So the pressure at minus L S minus the pressure at L S. That's it. Right. Okay. So I have these relations. Okay. So this is what's happening. So I have this one, that one, that one, and that one. Okay. Now the current in the initial state, the momentum at 0 in my initial condition is 0. So that goes to 0. Okay. Then I have this and that. And then the idea is simply to use a bit of physical argument here. If I take t very, very, very large going to infinity here, okay, well, I know that for L fixed and t going to infinity, that is going to be what at t goes to infinity, that's going to be the average p in the stationary state, constant for all x. T very large, for fixed L, that goes to the stationary state. So the left-hand side then is going to be 2L times the stationary state, average of the momentum. Okay. While the right-hand side, well, I don't know what it is. It's something a bit more complicated. Okay. But then if you think about that, suppose I have a pressure there, average of K left and average of K right here, and have temperature higher here than there, then the pressure should be higher. In relativistic QFT, that can be shown that the pressure is monotonic with the temperature. And what happened here? Well, I'm going to have some average of K stationary, which is going to be something in between, right? So okay, physically, I don't know exactly, but supposedly, I mean, intuitively, it should be something in between. So how does it go? The pressure from there to there, it should kind of change more or less monotonically from from something high to something in between, and here from something low to something in between. Now one can try to make these things more precise now that and put bounds now, but just with this idea, okay, you write this bit here as this bit here as well, okay. So you have something on the left minus something on the right, which is large. And as time evolves, it goes to something 0. So this is something positive throughout time, something positive. So we have from 0 to t is something positive. And in fact, from here to there is yeah. So let's say this is just something positive, greater than 0. Okay. Sorry, greater than, no, precisely. So more precisely. So there is this light cone. So this is really k left minus k right, all the way there, plus something positive what happened later in time that I don't know what happened. Okay. But is this k left minus k right all the way there, right? And that's multiplied by L all the way up to the light cone, essentially. Okay. So that will have the factor L k left minus k right, which is the bit of the integral from 0 to time equals L up to the light cone, plus the rest. The rest I don't know. I don't have much control over the rest. Okay, but I'm saying from physical argument, it's positive plus some constant which is greater than 0. Okay. And that's the thing. So essentially, you immediately get that relation that P you divide by 2L by 2. So you get P is greater than k left minus k right over 2. So just by a simple argument, using the light cone and using a simple idea about how pressure should change in space-time, you get a non-trivial inequality for the stationary current. And a similar inequality you can do on the other side by using the other conservation law for an upper bound. So, the interesting is perhaps the lower bound means you must have a current in general, if this general intuition is correct, if you have a difference of pressures on the left hand. Okay, so that's okay. Somehow we're wondering at the beginning about is it a non-equilibrium steady state that we get, or is it diffusive and all that and all this, right? If you have that structure, relativistic invariant, look at energy, it is not diffusive. You have a true non-equilibrium steady state emerging. You must have a non-zero stationary current, and so it's not time reversal invariance and all that. Okay. So this is showing that you have ballistic transport in general when you have a relativistic invariance. I use P equals the current of energy equals the density momentum. So for energy transport, relativistic invariance, you have ballistic transport. Okay, it's not diffusive. It is ballistic. So this is actually the general situation. Whenever you have currents which are functions of densities, constant densities, I mean, with appropriate properties. So like if you have densities which are of same type as current, like time reversal, antisymmetric, for instance. Maybe they don't need to be equal, but if they're of same type, then that will lead to non-trivial average values of these currents at large time and ballistic transport. Okay. But this is kind of just to show, in general, in a relativistic model, you must have ballistic transport for energy, and you have a lower bound for the current. Okay. Now, what are these currents? How do you calculate them? Okay. This is just a general lower bound with some general idea. You could make it more precise. Well, to calculate precisely what this stationary current is, and to get it more, kind of more physical about what's happening, what you have to use is hydrodynamics. Okay? So you have to consider such conservation laws and say a bit more about these things. So really, it's conservation laws at the level of averages after time evolution, and say a bit more about these things. In 1+1 DCFT, we could write the conservation laws for the fundamental observable themselves, the microscopic observables, right? We write explicitly and solve that. No, it's very, very simple. But in general, it's complicated. You don't know what K looks like. I mean, the microscopic observables are just complicated. They don't close among themselves in conservation law, okay? But you can write averages, okay? And the idea of hydrodynamics is to just simplify the problem at the level of the averages. And the way you simplify is that you kind of make sure that you close the system of equations. So in CFT, we didn't have to take averages to close the system of equations. dt t plus dt plus dxt equals 0, and dt minus dxt bar equals 0. So it closes them on themselves microscopically. Okay? Just need t and t bar, nothing else. But in general, it's not true. K is something complicated. But then at the level of averages, Hydro says that, well, maybe we can write this average as a function of the other averages that are there, and then close the equation and get something that is tractable. Okay? Now, what is the physical principle? Well, physical principle is that it's often called local thermodynamic. It's actually not a very good way to call it, but if you look on Wikipedia, actually, you will find that. Well, maybe Wikipedia maybe is not the best, but so you might find that in books as well. Okay. So what it means, it says that, well, you want to evaluate averages of observables in space-time, evolving space-time from the initial state, which is that, t left, t right initial state or anything else. And so you don't know what it is, but what you say is that actually, this is the many-body system, okay? So things evolve in time, okay? And I'm looking locally somewhere in space-time. I'm looking, say, here or there, and things change kind of smoothly. Like here, the pressure changes smoothly from high to something medium. Things change smoothly in space-time with luck, okay? Maybe it should change smoothly. And so locally, the state that you see should look like a stationary homogeneous state, something that has maximized entropy, like the things that we're looking at the beginning, right? So this is locally a maximum entropy state. Maximum entropy state at x, yeah. So this is a good question. Not necessarily, right? You may have a front there. You may have shocks. You may have all kinds of things happening. Yeah, that's correct. So I'm hoping that maybe like almost everywhere, let's say, but not at the light cone in general. Yes, indeed. So that will break somehow near the light cone. Then we have to consider how it breaks. And this is interesting to consider how it breaks, indeed. Yes. But so I mean that will have to be dealt with. This kind of singularity, but it can be dealt with eventually. If it's smooth, nice, almost everywhere, it's actually not too bad. It's okay. We can do something. Okay. Locally, it's a maximum entropy state that depends on where you look at in space-time. Right? So that's the idea of hydrodynamics, the local entropy maximization. Now we know what is entropy maximization. That means that locally we have something like exponential minus this beta I qi that I was writing at the beginning, right? So all the conserved charges being involved, right? But now the beta i's, well, they depend where you look. So they depend on x and t, and then you put this observable. And of course, what I mean is always the limit when L goes to infinity. So I look at local observables. I take a density matrix on an infinite space, and then I evaluate local observables there. That's my average. Like the stationary state average I was doing, right? This was an infinite volume average, but just for local observables, for a family of local observables. Okay. So maximum entropy state, well, maximum entropy with respect to the conserved quantities, of course. So I need to know what the conserved quantities are, all the conserved quantities. So I have to have some kind of completeness, right? So if I miss some conserved quantities, the equations I get are just wrong. And that's a typical mistake that people do in this area, that you don't know all the conserved quantities, you write some equation, it's incorrect. So you have to have them all, and it's not completely clear what it means to have them all, actually. And in fact, that answer that question I will answer partially in my seminar on Thursday, I think is my seminar. It's kind of slightly different context. But give a partial answer to the thing, not the full thing, but at the linearized level. One can give a full answer at the linearized level of what are all these conserved quantities. Okay. But for now, we say, okay, so we have to find them out somehow. Okay. These are all the quantities that are extensive. That's kind of the idea. So there should be some kind of conserved density, local enough in space or something, and you should be able to write that, and then you put that in. Okay. So this is the hydrodynamic approximation. It's an approximation, should be valid maybe at large enough time, when things are smooth enough and all that. In CFT, this is for the VRA0 sector, this is exact. It's true, right? There's a jump at the light cone, but in between, this is always true with something that is constant in between and, T left, T right, and stationary. Okay? So you generalize that. You say, well, let me assume that's always true everywhere in space-time. This is the Hydro approximation. And you would like to deduce a dynamics from that. This is an approximation for local observables, but it doesn't tell you how to evolve things now. But what it does something very important, that it reduces the number of degrees of freedom to just the concept of quantities, right? So a priori, you have to evaluate all the local observables know the state. So infinity many, but a large infinity, right? 2 to the n if you have n sides and, spin half on each side, something like that. But or 4 to the n, all the local observables, right? So it's a lot of things to evaluate. But now you say, well, all you have to do is evaluate, you just have to calculate all the beta i's. You reduce the degrees of freedom with the beta I. If you have 3 conserved quantities, as is typical of relativistic invariant non-integrable systems, because you have, well, you actually have 2, sorry, 2. Galilean, you'd have 3. Relativistic, you have 2, the energy and the momentum, that's it, okay? So you just have 2 conserved charge put there, the energy and the momentum, and that's it. So you reduce a lot, 2 functions, right? 2 functions of x and t. And, okay, so that's reduction. Now, what dynamics do you write? Well, the dynamics is very simple. Dynamics is the one that I've written there to get these, I had forgotten equals 0. It was here, right? Sorry about that. Equals 0. Dynamics is this thing that I had written there, okay? Is the conservation equation, right? So, of course, conservation equations are true always, macroscopically, and anytime, anywhere in time, space-time, no matter the initial state. It's a true thing. It's just from the dynamics. So, from the macroscopic dynamics. So, you have dt of qi, initial state, plus dx of the related currents. That must be equal to 0 for all i's, right? For all the conserved densities you have, for all i's. And now you use the, let's say, approximately imply or something, the Hydrodynamic approximation. So this is now dt of qi in this maximal entropy state. So that depends on the betas of xt plus dx of ji that depends on beta of xt. And that must be equal to 0. So now you have as many equations for i's as you have betas. Okay? That's right. So you have as many equations. You have a equation for every conservation law, and you have a beta for every conserved quantity. So you have as many equations as you have unknowns, and that's your system of equations. As many, this is kind of important, equation as unknown function. These are the Hydro equation. In fact, these are the Euler scale, say, or Euler Hydro equation. It's the Euler hydrodynamics because I have made this very strong assumption that there's local entropy maximization, full maximization. In fact, in reality, it's not quite true. You might have additional terms, and full hydrodynamics is actually a derivative expansion. So you add the higher derivative terms there. So so the average observable is not just that, it's that plus derivatives of beta. That's what. And what are these higher derivative terms? Then you have to use Kubo formula and all kind of formulas to evaluate that. But that's kind of another story. For now, just at the level of hydrodynamics, this is it. These are the equations that you want to solve. Okay? So now you just put your initial condition, qi on the left and on the right. You kind of know what it is. Suppose you can calculate, average and equilibrium states. Okay? And then you put that in here and you solve it. What's important is that the currents here, you have to write them, you have to know them in maximal entropy states, in these equilibrium states. But they're not necessarily equilibrium, by the way, right? They could involve the momentum and all that, but there's maximal entropy state. Okay? So you have to know all the currents and all the densities in these maximal entropy states. Now, of course, from basic thermodynamics, if you know the free energy, which you can often calculate, the free energy, which is F equals minus 1 over L log of the partition function at L goes to infinity. This is the free energy density. Okay? Well, you can calculate then the average densities, Qi, at any point in space-time. This is now a maximal entropy state. It's a stationary because it's involves the concept of quantities, and it's homogeneous because concept of quantities are homogeneous, that sort. Okay, I can put that in the point. So this Qi in this maximal entropy state is nothing else but the derivative of f with respect to beta I. So okay, so if you know the free energy in terms of all these betas, and sometimes you can calculate that, well, then you know all the average densities. Okay. But what about the JIs? Well, you don't know. You don't know. There's no partition function for the currents. So the JIs, a function of betas, this is a non-trivial thing that you must declare. These are the equations of states. These are the things additional to standard thermodynamics that you must know in order to do hydrodynamics, or hydrodynamics. Okay? The currents, the average currents. Okay? In CFT, we knew the average currents because, well, one of them is the density, right, the momentum, and because by tracelessness, the other, the pressure, was also just the energy. Okay? That's in CFT. But in general, then you don't know. You've got to calculate it. Okay? So that's the idea. So this is the general kind of setup going beyond CFT in order to solve this kind of initial value problem using hydrodynamic ideas. Okay? Well, it depends how lucky you are. If maybe you can calculate them exactly somehow. If you cannot, yeah, you've got to model. I mean, yeah, let's see. In fact, if you know the free energy as function of all the betas, then there is a general result of ours. Maybe there's some result before also, I don't know. But if you know that, if you just have 2 or 3 constant quantities, well, then actually you can calculate which is, in fact. So it's okay. It's not too bad. You can eventually get there. For instance, you can use the relativistic variance and all that stuff, and then you can calculate. For instance, in typical Galilean system, the pressure, even in relative system, the pressure is equal to the free energy. This is a general thermodynamic relation. Pressure equals F, you know. And the pressure is nothing else but the momentum current. So that's it. So you have it, you know. Actually, it's not too bad. But this being said, this was not known in integrable systems. Because in integrable systems, well, yeah, the pressure is the energy density, but then what about the current of the nth conserved quantity, which is some weird thing, you know. But you don't know how to calculate. So people didn't know how to calculate that. So here, this is a general formalism, and it should be applicable no matter how many conserved quantities you have and what they are, as long as you put them out, okay? Then that should be the correct thing. And once you have that, if you can calculate the currents, then you have your equation. That should be the correct large-scale description of your system. It's large scale, right? It's not microscopic, but large space-time, it should be correct. Okay? That's the general idea. Okay? So it's kind of a very powerful idea in the sense that, you see, for hydrodynamics, Earl hydro, you don't need chaos or anything like that. It's not about thermalization per se. It's not that. It's about relaxation, about the system that relaxes locally to something. And if you know where it can relax to, then you can write an equation. So it may be that it's a manifold, actually. I mean, full structure is not completely understood, but somehow these conserved quantities, they're like a tangent to the manifold. The betas kind of bring you along the manifold of all the states and all that. So this manifold of states may be very large, right? Infinite dimensional, or very small, or whatever. But whatever it is, once you have its structure and the density currents, then you write this and you have the large scale equation. It's interesting. You can even do that for free models. So let me just see what, yeah. So, and I want to give some examples indeed of how this works. Okay. So there's a few things one can say actually before that. It's very interesting. It's kind of very beautiful theory that I think which should be taught in basic courses. I think at university, but there's a lot of nice relation that emerge from this early hydrodynamics. Okay. So the first thing, before I give the example, I'm going to give some example. But the first thing is, what is this equation of state, right? The current. So usually, I mean, very often, this is actually written as a function of the average density. Okay? So instead of a function of the betas, I put, well, it doesn't matter, the average. Instead of a function of the betas are not so natural physically, right? So somehow the average energy is more natural than the local temperature, which is kind of a bit weirder to define something. So the average energy, momentum, and all that. So you can write a function of the local densities. That is, it's a bijective map in the appropriate subspace between the QIs and the beta i's. Okay, there's a bijection between these two things. Okay. In fact, locally, the fact that there's a bijection is not too hard to see. And one thing that you do, you construct the so-called C matrix, which is static correlation matrix. It's just susceptibility matrix. Susceptibility. So this is just the derivative with respect to beta j of qi, okay? And mu with a minus sign. So you just bring down the total jth conserved quantities when you do that. Okay? So that's just qj total conserved quantity, qi, and it's a connected correlation function because when you take the derivative, there's a betas in the numerator and denominator because of the normalization of the state, trace minus beta h. Okay? So you get the connected correlation function, qj, qi. Okay? So this is a symmetric matrix. By the fact that Q is conserved, I can bring it through, put it there, symmetric, and the X integral, I can put it by the fact that the state is homogeneous, I can put it on either the J or the I. This is symmetric matrix. And more than that, in fact, this is a positive matrix. So C as a matrix is non-negative. So because if you do kind of so AI, Cij, Aj, what you get is just AI, Qj, Qi, Aj, Aj, oh, Qi, Qj, okay, Aj, and and this, so this is, if I write it explicitly, integration dx, Qi of x, Qj of 0, average connected Aj, okay, sum over j's. And I have an integration dx here from, say, from 0 to L by using homogeneity, or imagine that the system is periodic, for instance, right? Then you can also integrate over the other variable, like average over the basic position there. So you can write it as AI, then 1 over L, and have two integrals, dx and dy, and have Qi of x, Qj of y connected. Aj. So this is now Qi, Qj. So this is average of, well, the square of an operator. Ai, Qi, Aj, Qj. So that's positive. If the operator is Hermitian, the square is positive. Okay. So this must be non-zero. So in fact, that matrix is well, non-negative. I think it's non-negative. Okay. And in fact, it must be strictly positive. If it had some negative bit, some zero bit, some zero eigenvalue, then that would mean that you have chosen a wrong conserved quantity that is 0, that doesn't have any effect, that should just be taken out. It's kind of the idea. Okay? So somehow you like a tangent direction in your manifold that's actually not a tangent direction. It doesn't go anywhere. It doesn't make you move on the manifold because the dd beta is 0, so no beta derivative. Okay? So it must be strictly positive. So this is the C matrix. And because it's positive, then there's, at least locally, bijection. Okay, so that's the idea. Okay? So bijection, so you can think of the currents or any observables as function of Qs, and then you can do the dji, dqk, say, okay? By just chain rule, you can write that. And this is the so-called Flux Jacobian. And that is the thing that's important in a lot of the Euler hydrodynamics, because then you can rewrite everything like your Euler hydro equation in terms of this flux Jacobian and the conserved density only. So dtqi plus aik dxqk equals 0. Okay. So this is the so-called quasi-linear form of the Euler equation. It's quasi-linear. It's linear in the derivatives. Of course, non-linear in general, because the flux Jacobian is a function of the state hence a non-trivial function of the densities, right? This function of the densities, and okay. So this is really the Earle-Hydro equation that one should solve, and that replaces what we've done in CFT essentially. Okay. Now, some general thing we can say about that, and I'm not going to prove everything, but it's actually not hard to prove. A lot of nice things about this. So this Flux Jacobian encodes all of the physics of the Euler scale. Okay? So in particular, you can try to diagonalize this equation. You can change variable. Okay? So suppose you find, so you write your Qi as some function of some other variable. I call it the nj's. Okay? So how the nj's. Okay? So I change variable. So Qi some other variable. Okay? Well, I can always do that. I can put that in this equation. Okay? Now I can take the Jacobian of that transformation. So d Qi d nj. That's some matrix Rij, some matrix. Okay? I put that in this equation. What I find is the same structure of equation with a similarity transform of the Flux Jacobian. So same structure. As I find dt ni plus r inverse ar ij dx nj equals 0. Okay, same form. So maybe I haven't done very much, but if I can find the f such that r is the thing that diagonalizes A, then I've diagonalized this equation. So if this is some diagonal matrix, say diag of some diagonal element, which I call V effective, some velocities, V effective, then these NIs are the so-called normal mode. So they're called Riemann normal mode, I think. So if you can find, it's not always possible to find these things, but if you can find them, then you have diagonalized your equation of dynamics. Okay. Now this is useful, it's nice. Of course, you see this has the form now dtn plus vf dxn equals 0. So it has the form of it's a bit like the Burger's equation, if you know about Burger's equation. It has the form of a dt something plus a nonlinear dx same thing. Okay. You can solve that by characteristic. Then you can find, essentially you can just look at this velocity, follow the velocity, and the value of n at one point in space-time is the value it had earlier in time, just following the velocities, these effective velocities. So you have this form of characteristics in space-time. So if you have my space-time now, time going up this time, okay? So I have some n value there at xt. I want to know what it is. I just have to follow, I don't know, kind of the whatever line that is parallel to the local effective velocities everywhere, and look at the value that's there, and is that value that it takes. So if you know the initial values, you can know that. Of course, you have to find what these velocities are, and they depend on n non-trivially. So it's kind of a non-trivial system still, but still it has a nice structure, right? So this solution by characteristic that comes out from this diagonal equation. Okay? In CFT, it's so simple. A is 0, 1, 1, 0, constant. You can do linear transformation to diagonalize it. So N0 is H plus P is just what I was calling T, and N1, say, is T bar. T and T bar are the normal mode, well, the average of these things, okay? These are the normal modes. T and T bar are normal modes of the CFT or Hydro. And everything follows. And these characteristics are just a straight line going back to the initial state that I was showing at the beginning for the solution to the stationary state. Just a generalization of this CFT picture. It's a bit more complicated, but see the same ideas, okay? But non-linear. Because now the Flux Jacobian in general depends on the state. And by the way, so the definition of a free system, you may wonder, so what is a free system in general? What does it mean free current, free boson, and all that? So the nicest definition, in my opinion, is a system where the flux Jacobian is constant and it's free. And then you can solve everything. It's free from the point of view of hydrodynamics, for sure. If it's not constant, not free. So CFT is free in the Virasoro sector from that perspective. Okay. Any questions about this? Yes, yes, yes. Indeed, indeed. So this is, you see, the question of particles and quasi-particles is very interesting. So once you do the hydro, the quasi-particles, what they are, is the normal modes. So these are the particles of your earlier scale. In CFT, these are the basic particles of CFT. You know, kind of this asymptotic particles that you can define in these masses theory. You can define them. Okay. So now you have something general, and now the point is you have to find what are these modes and what is the Flux Jacobian and how this whole thing works for a given example. You know. Sorry. Yeah. Yes. Yeah. So okay, I can do that with free theories out of that. And what you think of a particle in a free theory, what is normal modes? So it kind of all works out very nicely. Maybe I give maybe I give the example of the free theory. I think I could give the higher D CFT example, but it's a bit technical. So for higher D CFT, you can kind of restrict that to 1 + 1D by just looking at currents going in one direction. No, but of course, the stress tensor in higher D is traceless in higher D. So the bit of the stress tensor just in the 1 + 1D is not traceless, it's something else. So you have a non-trivial pressure, but it's not so complicated. In the end, the pressure is still proportional to the energy, but with a constant that depends on dimension, if I remember correctly. Like pressure is V times Z or something like that. So it's just a small change of the equation of state, okay? And you put all that in it, and then you can solve that. You have a flux Jacobian that's a bit more complicated, that depends on the state, and then you can do the whole thing. Okay. So the one thing he was talking about, the light cone and all that. So if I want to solve, the problem of kind of left-right and all that. So if I have this problem, okay, I have this thing there. So I have T left and T right. Start there. Now this initial state is actually scale invariant because it's the same everywhere. All x, there's a 0 where it changes the same everywhere in all x. Because it's the same as the initial state at x and at lambda x is the same. So it's scale invariant initial state. Actually, it's not CFT, but it's a scale invariant at the level of local averages, right? For all local averages. So as I evolve, then the Euler equation itself, as well, say like that form, is also scale invariant in space-time. No, because it's dt there and dx there, same power. Okay? So Euler hydrodynamics is scale invariant. It's not CFT, but it's scale invariant, right? At least with scale transformation. It doesn't have the structure of CFT now, but still. It has that invariance. So initial condition is scale invariance and final condition. So that means that the whole solution is going to be ray dependent only, scale invariant with respect to 0. Okay? So all the averages of all conserved densities in space-time, they will depend just on some ray. So eta is x over t. So which ray you look at. Okay? When you put that in this equation, what you get is a very simple equation. If you find the normal modes now of that, just get it right. What you find is that VI effective minus eta times d eta of ni must be equal to 0 for all I. So what you find is some kind of eigenvalue equation, and you find that this n, either it doesn't change, or the ray at which you look at is equal to one of these effective velocity at that state. And this is the situation in generic system. So typically what you're going to have is going to have no change, then a shock somewhere in some velocity, or maybe a discontinuity at some, that dvs, and then no change. And then you may have what they call a rarefaction fan, where somehow you manage to change your n just in the right way so that this relation stays valid kind of everywhere for a whole fan of eta. As you change eta, the VF changes as well, and you kind of manage to make that correct. So looking at that equation, then you get a kind of non-trivial structure in space-time of where it changes, where it doesn't change. And that depends on flux Jacobian, which is the spectrum of the A matrix of this, so VF, which is the spectrum of the A matrix, and the various the structure of this hydrodynamics. So anyway, I don't want to. There's a whole theory of that equation. In particular, it's very beautiful, hyperbolic equations and the solution for the Riemann problem, and that problem there for this equation is the Riemann problem of hydrodynamics. Books written about that. It's very nice. Okay. In particular, you can have shocks and all that. Okay. So I don't want to go into this details of that. In particular, so in higher DCFT, that's what you have to do. You have to look at shocks, rarefaction fan, and how the theory of hyperbolic equations. Essentially, you go in the books, and in our papers originally we hadn't gone in the books, and we had found a solution. It was incorrect. And if you go in the books, you realize, oh no, that's not quite the correct solution. Then you have to do this and that, which we did eventually. Okay, so now, but for free models, you can also do the same thing. So there's then you can write this equation and all that. But how do you do for a free model, free particles model? Well, suppose my Hamiltonian has that structure. Now I'm gonna be kind of maybe a bit less precise, but okay. I have these creation annihilation operator A dagger P AP. Hamiltonian have this form times some energy EP, some dispersion relation. Okay. And maybe my fermions, they look like that. Cx is equal to integration EP to the IPX AP, maybe 1 over the square root of 2 pi to have the right normalization. And then everything is normalized in the usual fashion and all that. Okay. So I construct this free fermion model for some dispersion relation. P squared is going to be a Galilean model. If I wanted to be relativistic, actually, I would have to do the Dirac matrices and all that, but I don't want to do Dirac matrices. Okay. So this is just a nice little free fermion models. And of course, this is a conserved quantity. The momentum is also a conserved quantity, just a question of dp. P, A dagger P, AP, the number of particles. Any power of momentum there is going to be conserved quantity. Okay? Now, and all these powers of momentum, so like the Qn, something like that, the question dp, P to the n, A dagger P, AP. That's also a conserved quantity for any P to the n. And it can be written as integration over x, psi dagger x, and then minus I d to the n psi of x. So this is actually a nice extensive conserved quantity with a local density. This is my Qn of x, my local density. Okay. So that's this is a very simple free fermion model, right? It's completely straightforward, direct, just Fourier transform and stuff, right? There's nothing complicated in there. And I can do that. This is perfectly fine. Many body system, local Hamiltonian, local conserved quantities with all these conservation. So now I can apply Early hydrodynamics on that, right? With all these conserved quantities, okay? And now I have infinitely many conserved quantities. So how do I do that, infinitely many conserved quantities? Well, I have infinitely many betas, right? So I have exponential minus beta n Qn, that's my kind of maximal entropy state. It's a GGE, a generalized Gibbs symbol, called GGE. Okay, I can write explicitly the exponential integration dp, and then there's some function w of p, A dagger p, AP. Okay, and that function is just sum over n, beta n, sum over n, beta n, p to the n, I guess, something like that. Yes, it's just that. Some function. Well, these are okay. Beta n, I put it there. Some coefficient. So this is a GGE, and then I can calculate conserved densities and all that. Now the question arises. So I can calculate all these average of Qn. It's simple to evaluate. Just Wick's theorem and all that. Okay. There's an answer you can write explicitly. It should be p, and I guess it's 1 over. There's a Fermi factor minus w of p. And there's a p to the n, I think. It would be a factor of 2 pi, something. Probably factor of 2 pi, or something like that. I'm not sure. So something like this, right? So this is the Fermi factor that tells me how many particles I have for this momentum. And then for each particle, well, how much, of this conserved quantity it carries. Okay? You can calculate explicitly with the traits, with the free fermion system and all that. Okay, so that's good. But what about the average currents? I have the average density, I need the average current. Right? So, I mean, this can be calculated. It's an exercise you can do. You know the exact average density. You do dt of that. You get something bilinear in the size. Okay? You write it as dx of something, and you will be able to do that. And that something is a current, it's bilinear in the size. You use Wick theorem to calculate the trace with that density matrix. So it's all doable in maybe 2 pages, I don't know, something like that. Actually, I haven't done it, but people who have done it, yeah. It's all doable. Okay. But what's the result? Well, the result actually is relatively simple. You can calculate it like this, you can calculate it in other ways. But let me just express the result. Let me just 1/2 pi again. So you have integration dp, p to the n, again this, okay? But the result is very simple. All you have to do is multiply this by what? Maybe you can guess it. The current is this and this. The current is the density times what? Times. You don't need to know. I don't think I would have guessed if I was a student like that. So you just have to put E prime of P, the dispersion relation, the group velocity E prime of P. That's a calculation that you can do explicitly. There are different methods, in fact, to do the calculation, not explicitly, implicitly, that gives you that, okay? But for now, let's think about that as a calculation that you do explicitly. Okay, so this is that. Now that I have that, well, I can write down my hydrodynamic equations. So I have to write down, well, I have all these conserved quantities, Pn, and all that, and all of that. And so why don't I write this as, integration dp, some p to the n, and then some density rho of p. This is that thing, right? W. And that's integration dp, there's p to the n, there's the velocity, v of p, rho of p, okay? Some density. So now, okay, so I have infinitely many equations, right? Infinitely many, with all the n's, right? But where is the space-time dependence? In the betas. Where are the betas? They're in the W, so W, where's W? In the rho. So rho is space-time dependent. So what I do, moving, so for hydro, I do rho is now a function of P, X, and T. This is my local state. And think of rho as being my local state and kind of any function of P there, X and T, right? Yeah, local states, the betas are there. And then I write the equation. So I have integration dp, p to the n, I have dt rho minus v of p dx rho equals 0. This is my Hydro equation, dtqn plus dxjn equals 0. And that should be valid for all n. So what do I conclude from that? Well, I conclude that, well, this should be orthogonal to Pn in the L2 space or something. I don't know. What I conclude is simply that this is 0. So I conclude that I have an equation for a phase space density, rho px t. An equation is nothing else but Liouville equation, isn't it? Liouville equation in phase space. You know, Liouville equation when you have 3 particles and you have conservation of phase space elements for 3 particles. This is conservation of phase space element. So the Liouville equation for 3 particles going in phase space. And they all go at velocity v of p. So the free fermion, I could have done the free boson as well. The earlier hydrodynamics is the Liouville equation of phase space conservation. So it's a kind of nice reinterpretation of this basic equation. Okay? And this is true. So that's now this was derived from hydro perspective, but you can prove that it's correct at large scales in the free fermion system. Yeah, so 5 minutes? Yes, excellent. So you can, yes, sorry. Yes, so from there to there, yes. And in fact, P to the n, they're not quite complete, actually. They are not. In fact, there are many more conserved quantities than these. You can put here a non-trivial kernel of x and y, or x minus y. Have an x and a y there. And as long as x minus y decays sufficiently and has the right properties for being conserved quantities, that will work. And there are infinitely many conserved quantities like this. So there are many, many more. There's a continuum. And that's why you can actually do that. You can go to a continuum. Yes, exactly. This is the last bit. Now maybe I described that then at the beginning of next class. Then yeah, I think that would be the best. I thought I would finish, but okay, of course it was a bit too much. Yeah, you can redo all of that for integrable systems. And the trick in integrable system, the non-trivial bit you see, for integrable system, these average densities are known for a long time, actually. This is from thermodynamic Bethe something similar to that with the pseudo energy that's there. But the average currents, see, I said, well, you have to do that. Well, we don't know in LS, for instance, we don't know how to write them explicitly. Well, there's some trick to generate them. But then how to write the currents, how to calculate the current, that is hard, okay? So you need some other tricks, and there are other tricks. And then you can write that also in the TBA form, thermodynamic Bethe form. So you can use the old result that people have, right? Use the tricks, write the currents, do that, and get an equation. And that's this generalized hydrodynamics equation. And then from that allows you to solve this initial value problem. And here you see this is directly in the normal mode form, diagonal form, right? With the V of P being this V effective. So the V of P are the spectrum of the Flux Jacobian in free models. Right? It's immediately normal form. And in integrable system, one can also write the normal form and find the right spectrum, V effective of P and all that. And you see that these modes, the I and I, they are the particles, the momenta, the P's. So the quasi-particles are the hydro modes. In free models, same thing also in integrable models. Yeah. And yeah, then you can just solve, I finished there, you can solve that equation quite explicitly. And all you have to do is the particle of momentum, the row of P, X, T, you evolve it back at its velocity P. And in free model, it's just straight line. See where it goes. If it's on the right, then it's T right. If it's on the left, then it's T left, right? It's kind of temperature, that particle as if it was in the left, T left temperature or T right temperature. And you know how to do that because this is explicitly, you have a separation of temperature for every mode there. So you kind of know explicitly what to write. So you have an explicit form, and also similar, you have something relatively explicit in integral models as well. So you solve the Riemann problem. So that's the idea of Hydro. It goes beyond the CFT. I think that's it. I stop for now. Thank you. Yeah.
So, as you know, for two terminals in 1D, you quenches, and
yeah.
then interpret the entanglement group as this, so the particle
yes.
propagate and
yes. Yeah.
So, can you directly
yes.
So the particle entanglement?
Yes, the answer is yes. So this is actually an interesting question. So in free model, you can see that even in integral models, there's also this entanglement growth and all that with interpretation in terms of quasi-particles. And that involves exactly the Flux Jacobian spectrum. And so the quasi-particles have these velocities. Okay? And now the full relation, like the proof of this picture from hydrodynamics is not really yet done. So we're kind of working on that, kind of the hydro re-understanding, but the formula is already there. And it's the same object that are involved. But the kind of proof using hydrodynamic ideas actually requires fluctuations, studying fluctuations, because it's entanglements versus fluctuations. So it requires studying fluctuation, not just averages of local observables. It's non-local. So you need to go a bit further, but it's the same idea. Yeah, so this is also a very good question, actually. So it strongly depends on the initial state. So this is like quenches, where you have some initial state and you suddenly change it, and then you have particles now. So it depends on the initial state. The initial state, if it emits pair of particles, then you can deal with that. If not, if it's more complicated, then it's a bit less clear. And otherwise, what other properties requires? I mean, for integrable system is relatively general. Now I don't know, maybe there's some special cases. No, exactly. It's especially the initial state, as far as I understand right now, that is crucial to have a nice interpretation of the particles.